Video is going to be covering muscle mechanics and levers. So the first idea that we need to cover in muscle mechanics is the idea of torque. Hopefully you have had a physics class which has given you an idea about what torque is. Inside of the body there are many applications of torque because our joints act like a rotary force, a turning or a rotary force, a spinning force. So torque is force times the distance of the lever arm. Force times the moment arm. Okay? One more time. Torque equals force times the moment arm. And the moment arm is the shortest distance from the axis of rotation to the line of action of the force. So here's an example of that moment arm. The moment arm is the shortest distance, one more time, the shortest distance from the axis of rotation to the line of action of the force. So it's the shortest distance from the axis of rotation to the force. So there are some properties of torque. A magnitude, right? How big something is, the line of action, and this is something, we'll talk about this more in class, but this is something you're inherently familiar with. If we hold something in our hands close to our shoulders, the moment arm is much smaller than if we hold it at a 90-degree angle. So it feels like it weighs more when it's out here, when it's out at a 90-degree angle, as opposed to when we have it up. The point of application, so where our muscle attaches to a bone, and then the direction. So our levers are torques around a fulcrum. A little bit of trig. I'm not going to ask you guys to calculate, I'll leave that to your physics professors, but I put this in here. You can actually calculate the amount of torque around a joint, which is important for somebody who is interested in biomechanics. You can actually calculate the amount of torque on a joint to find out how much resistance or force your muscles are producing, and you can use that doing your trigonometric functions, so your sines, cosines, and tangents, if you remember back to those. Here are a couple proofs about torque. So this is the effective muscular component. So this is just showing that the muscular portion of torque is equal to force times the lever arm. So torque is equal to force by the lever arm. So this is just a proof showing that the effective muscular component is equal to torque. Torque equals force times the lever arm. Here's another proof that shows that the resistive component is also equal to torque is equal to force times the lever arm, the distance of the lever arm. So one more time, the resistive component is torque equals force times the lever arm. So when our muscle force and our resistive force are equal, we produce a contraction that is not moving or isometric, same length. When muscular force is equal to resistive force, we produce an isometric contraction. When muscular force is greater than resistive force, we produce a concentric contraction. And finally, when muscular force is less than resistive force, we produce an eccentric contraction. So an important note, force and torque are different because torque takes into account the lever arm. The force of something may always stay the same. If you pick up a 10-pound ball and you hold it in your hand, that ball is always 10 pounds no matter where it is, but the torque changes because the lever arm, the distance from our the distance from our moment arm to the axis of rotation will change. So force and torque are actually different because torque accounts for the distance of the moment arm. There are 3 different types of levers, and we find each of these types of levers in the body. However, the first and second types of levers we see very infrequently, but the third classification of lever we see often. So the first classification of levers is where the fulcrum is in between the effort and resistive torque. So let me show you here. It's when the fulcrum is in between the resistance and the force. That's what this is saying. The first class lever is when the fulcrum is in between those two things. So like we have in a teeter-totter, or pliers, or scissors. This is unusual in the musculoskeletal system. However, one example is the triceps. So we have the insertion of the triceps down here on the olecranon process of the ulna. We have the axis of rotation, and then the force will be out here at the hand and at the arm. So we have the axis of rotation between the force and the resistance. Here's a couple more examples. Up here in the head, the resistance is out here at the face. The force holding our head up is back here, and the axis of rotation is right here just off of the spine. Here's a teeter-totter, here's the scissors, the triceps. So that is a first class lever. A second class lever is where the resistive torque is between the fulcrum and the effort torques. So let's look at this picture here. So here's our axis of rotation out here at the balls of the feet. We have the resistance in between the force and the fulcrum. So that's what this is saying here. So the resistive torque is between the fulcrum and the effort. Again, this is unusual in the musculoskeletal system. It's kind of like a wheelbarrow or a nutcracker. We do this when we do a push-up. If you want to pause and do a push-up, you can imagine how the resistance is more at our belly button. Our force is out here at our arms, and the fulcrum is actually down at our feet. Here's a few more examples. So the gastrocnemius muscle, the resistance is going to be right here coming down through the sole of the foot, but the muscle is actually behind that. So the lever arm on this muscle is longer than the lever arm on the resistance, and we'll come back to that, but that's going to be important. So our final classification of lever is the third class, where the effort torque is between the fulcrum and the resistance. This is the most common type of lever in the body. So one more time, the effort, the motive force, is in between the resistance and the fulcrum. We have an example here of the biceps brachii. So this tendon of the biceps brachii is going to come down and insert on the radial tuberosity. The axis of rotation is here at the elbow, and the resistance in this example is out here at the hand. So you can see that this is a third type of lever. This is a diagram kind of comparing and contrasting the 3 types of levers in one graphic. If you need to, take a moment and just try to appreciate each of these. As we move down, a little bit more discussion about, why these levers matter. So the close proximity of the muscle attachments to the joints results in shorter force arms. This is like the third class of lever, okay? So the fact that the biceps brachii comes down and attaches close to the axis of rotation, making it a third class lever, lends itself to different advantages and disadvantages. So third class levers are built for range of motion advantages and speed advantages, and not necessarily for force advantages. So one more time, this third type of lever system, which is common in the body, is really good at producing range of motion and handling light loads. However, it's not very effective for handling heavy loads. It's not very good for force production because the moment arm on this muscle is much shorter than the moment arm on the resistance. So the resistance, if this is really heavy, the muscle has a tough time overcoming this lever arm. So the distance of the center of rotation of the joint to the point of attachment of the resistance to the limb or the forearm. So our resistance, this is just one more instant. We have our axis of rotation, we have our direction of pull with a short moment arm and a long moment arm with a resistance across here. Last couple slides here. So in our bodies, the mechanical advantage is equal to the motive force arm divided by the resistive force arm. In most instances, this motive force arm is going to be smaller than the resistive force arm because most of the lever systems in our body are third-class levers. So the mechanical advantage in these instances is to range of motion. However, I said most, right? We have an instance here in our second-class levers, or our gastrocnemius, where the moment arm on our force is longer than the resistive arm. Where this happens, the advantage is actually to force. So our gastrocnemius needs to produce less force than the weight of our body because it has a better moment arm than our body here. But again, in our third-class levers, anytime this happens, the moment arms favor the resistance. So if a muscle is the motive force, the muscle always has the mechanical disadvantage in force. But the musculoskeleton has a mechanical advantage in range of motion and speed. Now, I'm going to pause this video right here. We are going to cover this question and this next slide a little bit more in class so that we can talk a little bit more about these levers, and I want to put some practical application behind them, and then I want to talk about how they can actually change depending on what type of muscle contraction that we are doing. And that finishes this video on muscular mechanics and the lever systems in the body.